So in this series, we're going to look at sampling distribution of proportions. Now, in terms of the name of this section, we know these words. We know this idea of sampling, so we'll have this concept of taking samples. Distribution, we've been looking at probability distributions, so we should what we'll be looking for here is a nice bell-shaped curve that we can use, and we can use all of those tools that we just learned for working with normal distributions. So we want to create this distribution of samples, and then what we're going to focus on in this section is working with proportions. So the idea being that we'll have categorical data, and that we'll be looking at these kind of proportions of a sample size. So when you see proportion, that relates to like a percent of some sample size that we're looking at here. So let's talk about this example. And in this video, what I'm going to be showing you is just a simulation. So just to show you where these concepts come from, what is the idea that we're looking for here? And then from there, we can get into the calculation in the next videos. But this video is just purely a simulation to show you where these ideas come from. So what we're going to do is we're going to roll a fair die 60 times, and we want to find the proportion of ones that show up. So before we get into anything else, let me just give you an idea of the idea that we're going for here. So what I have here is a website. Random.org is great for just random generation and games and things like that with randomness involved. So I want to roll a die 60 times. So just for the long way of doing this, if I was in person, I would roll a die and hey, I got a 1. So there's 1, and I'm looking for ones here. I roll again. Well, now I've had 2 attempts, but only 1. Roll again, and it's taking a while, but it would be my 3rd attempt, and then if it's a 1, I would keep racking them up, but like this came out to be a 2, so now I just have this 1 out of 3. And the idea would be that I do this 60 times, which I'm not going to do in this video because that would take forever. So instead what I'm going to do, what's nice about this random.org is, and it has things like flipping a coin on here as well, but what I could do is set it so that it's going to roll just 60 dice at once. So this would be the idea of rolling a die 60 times, or doing it all at once would be the same thing since we have independence. And then what I'm interested in here is the proportion of ones. So the idea being, when we roll, we have this idea of our population proportion. We expect 1/6 of the rolls to be a 1 because it has this probability of 1 out of 6. Like when we flip a coin, we expect it to be 50-50. However, with random variation, that's not a guarantee. Like if you flip a coin 10 times, sure, you expect 5 heads, but maybe you get 6, maybe you get 4, and that's totally okay. It's not a sign that there's anything wrong with the coin. There's just this randomness to it. It's the same thing here. So if I roll a die 60 times and I expect 1/6 of those to be ones, it's like I'm expecting 10 ones. So if I count them up here, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So see, I landed a little bit above, but this is working with the idea of a fair die rolling, and we would be close to 10 out of 60, but having 12's just fine. So this would be my sample, and this is how we would collect it. So I had this proportion would be 12 out of 60, which I could translate to a percentage. So what I want us to think about, though, is what if I had this other sample? So I'm going to jump over to a sample that I already ran here that has kind of a more extreme case. So it's a fair die, rolled 60 times, and I got 1, 2, 3, 4 ones. Now that's quite a bit lower than 10. It's kind of an extreme example. And with that, I mean, this is a website, but say I was doing this with real dice, what I might start to think of is, ooh, what if my die isn't actually fair? What if it's weighted to show other numbers more than 1? So what I might be interested in is comparing how extreme is this example, given the fact that I expect this 1/6 probability, and coming from a sample size of 60. With those two pieces together, we want to see how samples should behave in that idea. And then we could get at this comparison of, well, where does our sample land? Is it expected or unexpected? So that's where we want to make a distribution of samples. What I would want to do is take that proportion that I would expect, take this sample size, and create a distribution of samples. So to create this distribution of samples, what we would start doing is just generating random samples. So like with this website, what I could do is collect the proportion from this sample, roll again, and then collect the proportion from this sample and collect the proportion from this sample. And what I would start doing is building a dot plot and see what does the distribution look like? Where is it centered? What's the standard deviation? So where we want to get at with these sampling distributions is where we start is we'll be given some population proportion. Like in this case, we have this population proportion of 1/6. So that would be P. And what we'll also have is some sample size, and we'll talk about the effects of sample size later in this video. So for us, we're using a sample size of 60. So with those two pieces, if I start randomly generating samples and make a number line and start mapping where they land, what we want to see is something that's bell-shaped. Because if it's bell-shaped, then we can use all of those tools for finding probabilities of certain events. So within this bell-shaped curve, what we're collecting is, if we did imagine this was a dot plot with all of these dots stacked in here, each dot would represent a sample proportion from a certain sample size. So for us, it would be one sample of 60, and then collecting the proportion of ones that we see within that sample. And so what we want is this distribution where we've collected this sample over and over and over again. So what we're going to go to here is the actual simulation where we can see this distribution form. So instead of just rolling those dice over and over again, which would take a very long time to make that dot plot, I have a program here. And again, these programs that I'm showing here, you don't ever need to use these. They're purely for the simulation sake. So don't worry about the programming that's going on in here. But this program, StatKey, and making a sampling distribution for a proportion, it's going to simulate exactly what I described there. So something that I've already put in here is I chose a sample size of 60, and then we'll play around with changing that and see how it changes. And then I also plugged in my population proportion in the decimal form of that 1/6. So that's my proportion of ones that I would expect. So what I'm going to do here is we're going to have some different windows. We'll have this original population, which actually is already set here. So that's just showing us our population proportion. So in fact, this original population, I'm going to fill in that information there because we're going to talk about the relationship between the windows. Original population is a set population proportion. So in that window, we're just showing what we expect for our proportions. Now what we're going to start doing is make samples. So we're going to start collecting sample proportions. So remember from our notation, P is a population proportion. So it's coming from population data, or in this case, it's coming from the structure of the thing. So the fact that it's a fair die brings to that 1/6. Then what we're moving to is the idea of taking a sample. So it's not necessarily going to behave like the population proportion. We expect the population proportion to come through, so there are going to be instances where those two numbers are the same, but like we were talking about with variability, it's not a guarantee, so we might see some change when we collect those sample proportions. So I have that original population, and what I'm going to do here is generate one sample. And all the things that happen there are two pieces. There's the sample and then the sampling dot plot of proportion. Oh, that's a mouthful. All right, in the sample, what they collected here was a random sample. So this essentially rolled a fair die 60 times, expecting this 1/6 proportion, but it accounts for random variability, so it has this count, so it saw 8 ones out of the 60 die rolls. So what that gave us was this proportion, so that 0.133, that's our sample proportion. So this window here for sample, it's just sample data, in this case from rolling a die 60 times, counting how many times it saw a 1, with the idea of expecting that population proportion but allowing for random variability, which gave us this value for p hat right here. So in that window there, that sample window, it simulates a sample of size n. In our case, we're using 60 for n, and shows our sample proportion, which in this case is counting how many ones did they see out of the 60 die rolls. So then our last piece here is this distribution of proportions window, or sampling dot plot of proportions. And what we can see is we have this one dot right here for that 0.133. So what they did is they collected a sample, they got a proportion out, and then what they're going to do is generate a dot plot so that if I go to make a second sample, so I'm going to go generate one sample again. So now it did same idea in the sample window, but now we just have a different sample. In this sample, they saw 15 ones come through, so it had a 0.25 sample proportion. So now we can see our dot at 0.25, and we still have our dot at 0.133. So we have these two different sample proportions showing up here. And if I generate another sample, we can see in this case they saw 10 out of 60. So this is that case where it lined up perfectly, which can happen. In fact, it's expected. But now we can start to see like this is landing where we expect it to, but then with random variation, we could be above and below a bit. So for this dot plot window, what we're doing is we have collected sample proportions from a sample size of 60. So with this distribution and seeing these dots come through, just think each dot represents a sample of 60. This dot right here is 60 die rolls, and that's where we saw the 0.133 proportion come through. This is a separate case of 60 die rolls, and it's the one that we just saw where they saw 10 out of 60. And then this case over here was a separate rolling of 60 dice, and they saw 15 out of 60, and that 0.25 came through. So with that, we can start to see how samples behave. And as you can imagine, I could just start clicking and just generating more and more samples. And this is where it's really nice to have a computer program just lay them out for us. And then you can even see, I'm going to use these shortcuts here where I can just have it generate 1,000 samples nice and quick for me so that it'll run this simulation basically 1,000 times. So when I push this button here, 1,000 more dots will come up. So just for a smaller idea of it, if I generate 10 samples, 10 more dots added in. But each dot is coming from this idea of sampling 60 and expecting that 0.1667, but with random variability coming through. And I could generate 10 more samples and 10 more dots came in. So let's go to this extreme of generate 1,000 samples. And we start to see something that is roughly bell-shaped, which is fantastic, exactly what we want. So what you can see here is we start to see our bell-shaped curve. It's roughly bell-shaped, which is what we want. Once we get this bell-shaped curve out, though, to use like our tool of using GeoGebra to find probabilities, what we want to do is we need to know mean and standard deviation. So the mean of this graph, so that's coming through in the upper right window here. So we can see samples. So that's just telling me how many dots are showing up here. So I have 1,034 dots here. So that's 1,034 times that I essentially rolled a fair die 60 times, and collected the proportion of ones. And it's these proportions, those sample proportions, that are being graphed here. Mean is 0.166, which is directly relating to our population proportion. Those should come out to be basically the same. And in fact, that'll be a rule that we use, is that those are going to be the same, because when we do this, we expect that population proportion. It should happen most often, and then we allow for variability to be above and below. And then we have standard error. That's just terminology that we'll talk about later. Really, it's standard deviation in this case. So standard deviation here, which is describing the spread of the graph. So this next question, look at the statistics posted on the upper right of the window. We're going to ignore the sample size there, because what we want to get to is this idea of running this infinitely many times. So if we did this infinitely many times, so then our sample size would be indescribable. So with that, we're just going to focus on mean and standard deviation. So the mean is describing the center of the graph. So it's the average of all of those dots. So what we're going to call this is the average of the sample proportions. Now, if we think of doing this in kind of an abstract way of doing this infinitely many times, this mean that we get out is actually a population mean. So with that, we use the notation of mu, but since this is specifically relating to the idea of taking sample proportions, that each of those dots represents a p hat, and we're averaging all of those p hat values, a little notation that we use is we use mu, but there will be this little subscript of a sample proportion, just to show that this is the average of sample proportions. And then what we're going to see is when we use this, if we want this average of the sample proportions, it's always going to be equal to your population proportion. So with that, and at the beginning of these problems, you'll always have your population proportion. So with that, you'll always be given the mean of this graph. Then for spread, they described it as standard error, but let's go ahead and switch it to standard deviation. So this is going to be the standard deviation of the sample proportions. So same idea, this will be a population value, because if we run this infinitely many times, then we'd have all of the information. So you're going to see the notation for our population standard deviation, and just like with the mean, because this is specific to sample proportions, we'll have a little p hat down there. Just to show it's the standard deviation of sample proportions. Now we're going to have a formula for actually calculating that from the information that we're given, but we're going to hold off on that until the next video. So describe the shape of the dot plot. Well, that came out to be a normal distribution, at least roughly. The more samples I'd run, the more it would smooth out. Like I could just keep hitting this 1000 button, and it would just become more and more bell-shaped. So now I'm at like 5,000 samples there, and it is very normally distributed. These gaps that are occurring is just because there are discrete outcomes for this. So they're kind of separated, but we're smoothing it out and we'll make it a continuous number line. And with that, it looks like a bell-shaped curve. So we have a normal distribution, and we'll have, with that distribution, the mean of the distribution will always be your population proportion, and really that mean symbol should have a little subscript of p hat. But when we go into GeoGebra and type things in, you won't have that symbol of p hat. And then standard deviation we'll talk about in the next video. But we'll have those two pieces, and then we'd have our distribution for how samples behave. So then, if I get to this point where I have a bell-shaped curve, and I could start talking about probabilities, and what we'd see is, in this case, it would be centered at that 1/6 probability. So we'd expect 0.1667 for my sample proportions, because that's what's in here. then we could start looking into that extreme sample that I saw, because we had a sample and it had 4 ones come out of the 60 die rolls. So it's like I collected a sample proportion of 4 out of 60. And just to get that onto our number line there, that's a 0.0667. So I could start thinking about how extreme is that? How far away is it? And that's where we could start looking at probability. So I could say, well, 0.0667 is out here. And then we could start talking about how low that probability is. In fact, we could even have it more accurate here. There's a number line on this graph. 0.0667 is about there. So we'd see is it's in this more, don't necessarily know if it's an outlier. That's something we'll talk about. And this is tapping in very closely to what we're going to do for hypothesis testing. But it's this idea of how extreme is it, and we can start to see that we're landing out in the tails in a region that's pretty unexpected for rolling a die 60 times. So a big part of the questions that we're going to be dealing with is starting with this case of defining our normal distribution, so defining our mean and standard deviation, so we can then go answer probability questions. So let's talk about sample size though. Let's compare to if I rolled a die 10 times versus rolling a die 100 times. So something that's going to come through here that we want to think about is that with smaller sample sizes, there's more extreme things that can happen. You get more outlier cases, like rolling a die 10 times. If I don't see a 1 at all during that, that is completely that could happen. It's not what's really expected, but it could happen, and I wouldn't be that surprised. Or like rolling 5 dice, so like playing Yahtzee, getting all 1s, not the most common thing to happen, but it's not totally unexpected. People get Yahtzees. So with that, with smaller sample size, these more extreme cases can occur. When we increase our sample size, so rolling a die 100 times, if I rolled a die 100 times and never saw a 1, that wouldn't sit right with me. I would think there was something really wrong with that die, because that's just so extreme. So it's the idea of not seeing 1s at all, this extreme case of like having a sample proportion of 0. When you have a small sample size, it's not that unexpected, but with a large sample size, very unexpected. So we want to keep that in mind when we look at this. So what I'm going to do is I'm going to change to a sample size of 10. So what we'll be doing here, and I'll just run one sample here, is now I'm rolling a die 10 times. I still expect a 1/6 probability. Here I saw 1 out of the 10 rolls, so 10%. If I do it again, that actually gave me the same proportion. Again, this time 2 out of 10 were 1s. So then I'm going to just go ahead and press that nice 1000 button. In fact, I'll just click it a few times so we can see. And we end up with something that is right skewed in this case. What you can see is, if you kind of imagine connecting those dots, something that's very right skewed. So we end up with this tail of data, and what that is really focusing around that 0.1667. So we really expect to be around there. Then we can see everything up to 50%. So we get something skewed. So with that, our data is skewed. And something that we talked about is that we want the normal distribution. We want something that's bell-shaped so that we can use all the tools that we have to calculate probabilities. If it's skewed, we can't do that. So that is not good. Whereas if I switch over to a sample size of 100, and start generating samples, there's our bell-shaped curve. So when we use large samples, it normalizes. It ends up creating this bell-shaped curve with that behavior of we expect to land at that 0.167, but we could go a little above, a little below. But when we have small sample sizes, it doesn't behave in that way because more extreme things can happen in those cases. So something we need to keep in mind is, let's see, large sample size, this was normally distributed, which is exactly what we wanted. Yay, that's good. So something that we're going to come across is we're going to have these conditions that we need to check before we can do this, basically to prove that we do have this bell-shaped curve. This is going to be called the central limit theorem. So some things we'll need to check for is we should have independence, which we do have when we roll dice, and that the probabilities aren't changing. If you roll 2 on the first roll, it's not going to affect the probabilities of the next roll. You should also have randomization, so some sort of random sample, so maybe like randomly selecting the die. But then something we're also going to have is to check this idea of, is our sample size large enough? And this condition is going to be called the success-failure condition. So basically, we want to make sure that it's large enough so that we can have at least 10 successes and at least 10 failures. So how we're going to do this is to check the successes, the number of successes. So like in the case of rolling a die 60 times, and the number of successes would be like, how many ones do I expect to get? Well, the probability of rolling a 1 is 1 out of 6, and then apply that to 60. So we'd multiply those two together, and I want that to be at least 10. So the notation we're going to use is, you'll see sample size times that population proportion, and that should be at least 10. So for our example up here, in fact, this is something we'll need to do before we even build our bell-shaped curve, because we'll need to make sure we have a bell-shaped curve, is for the central limit theorem. So independence and randomization I'll talk about, but really what I just want to see is that you think about it. So with the problems I give you, you can just go ahead and write down the words and then check those past those. So I'll talk about them, but I won't ask for proof. But with success failure, I will want to see the proof of it. So for success, taking the sample size times our probability of success, so 1 out of 6, which in this case is equal to 10, which is in fact more than or equal to 10. So we're good for the successes, but we also need to check the failures. So some notation we're going to see here it's kind of linking to binomial. So if P is our probability of success, then Q is our probability of failure. So we'd want to make sure that that is also more than or equal to 10. So just keep in mind that if you're working with Q is just 1 minus that probability of success. So for us, it would be the 1 minus 1/6. So this would be essentially taking 60 times 5 out of 6, which would be 50, which is also more than or equal to 10. So I chose 60 as a sample size specifically for this case because that met the bare minimum of sample size for this. So with that, we pass our third condition, which just guarantees that we do in fact have a bell-shaped curve, and then we can go forward with the tools that we know already. But if we fail any of these conditions, then we can't move forward because we might have something that's skewed, and if it's skewed, there's not much we can do with that. So when we go through examples, I'll show you this checking of the central limit theorem, but something that we need to think about, especially the success failure, because of the effect of sample size. All right, 2 quick little pieces here, just what in general happens to the sample proportions as the sample size gets larger. So we saw there, and in fact, we could even compare when we saw a sample size of 60. And I'm going to start generating, I'll go to 3,000 samples. You can see everything from about 0.05 up to 0.35. So you can see from that number line that we expect to be at that 0.167, but in terms of spread, or we can even just look at the spread of 0.047, we can see that things are spreading out by a 0.047. But if I increase my sample size, let's even go to a sample size of 150. So I'm rolling a die 150 times. So with that, we expect less variability. So now when I make my number line, notice that I'm closer in. This was 0.05 and 0.35 before, but now I can only see to 0.1 and 0.26. So we've kind of squeezed in around that population proportion. We still expect that 0.167. So with that, what happens to our sample proportions is that those sample proportions get closer to our population proportion. It's that we see more behavior lining up with what's expected when we have larger sample sizes. This connects to what we talked about in probability with the law of large numbers. Kind of the more you repeat a process, the more it behaves as you expected. And then what happens to standard deviation? Well, what we saw there, and I could even do a few more samples there, we have a smaller standard deviation. So again, bringing through that idea that there's less variability. So it decreases because there is less variability. All right, you made it. I know this is a long video, but this really does get at the foundation of our sampling distribution and where it's coming from. But just to summarize real quickly, it's going to be this idea that we're going to know a sample and an expected population proportion, but then to see how samples in general behave, what we'll do first is we'll need to think about the central limit theorem, making sure that we're taking a large enough sample size. But then from there, we'll start to use this normal distribution based on the fact that when we build this sampling distribution, the center is always going to line up with your population proportion, and then standard deviation will be something that we can calculate. And then once we set up our normal distribution, we can go into questions involving probability, like this example we started talking about here.